So I made a programming language for my final project. And this is a program called Game of Life, written in my language. I know it's kind of an overkill for a final project, but isn't that fucking cool? Anyway, here's how I did it. If you're a CS student or just interested in CS in general, you've probably heard of the course Introduction to Computers. Basically, you learn how computer works from the ground up. Ones and zeros, bitwise gates, registers, memory, CPUs, so on and so forth. And that is one of the courses I intended this year. It has a final project that accounts for 25% of the final grade. Our course simply recommended some super safe option for it, like making a simple game in Python or just finishing the optional homework. But do you think I, an Asian student, would choose one of those inferior projects just to avoid suicidal thoughts during the final week? No, I want the drama, the spice, the unnecessarily complicated challenges. So I decided, you know what? I'm gonna make my own programming language. From scratch, of course. Sure, it's like signing up for a marathon after your first jog, but hey, I'm Asian. Overachieving is in the blood, right? And here we are. First of all, there's a problem. I have no idea how to make a compiler. Don't get me wrong, my course actually did explain how the typical compiler works, but it never taught us how to implement the thing. So my instinct is to Google how to make a compiler, because monkey see, monkey do. And I came across this tutorial. Let's make a teeny tiny compiler. And it says, the teeny tiny language you are going to implement is a dialect of Basic, and if I prefer C-like syntax, it will be trivial to modify the compiler at the end. Okay, looks like a great tutorial. I'ma just follow this one, I guess. Oh look, it even shows a diagram that's very similar to my courses. Let's go.
One eternity later.
Okay, I finished the lexer and the parser. Time for the emitter. The emitter is a component that will produce the compiled code. In this case, our compiler will be producing C code. Wait, it compiles to C? Why it didn't say in the beginning? Oh, it did say in the beginning. Come on, how do I explain to my Asian mom that my programming language only compiles to C code instead of a native executable? Just kidding, I saw that in the beginning, but I thought it was a good start for a monkey that had no idea how to implement anything. So I still finished the tutorial just for the practice. And after that, I came across this video series by Mr. Solding. It's basically about making a programming language in Python, and it compiles to x86-64 assembly. And holy shit, that is freaking cool. And again, monkey see, monkey do. So I finished the whole series, and essentially acquiring the knowledge of creating a compiler. So let's do that. Remember the tutorial said, if you prefer a C-like syntax, then it will be trivial to modify the compiler at the end? Well, that is the first thing I'm going to do. See those all capital keywords? I think that's pretty ugly, so I'm going to change it to lowercase. And I'm adding parentheses for function calls, change the repeat to do, change this and well to just and that's kind of like Lua. Matter of fact is 90% Lua, but we can change it to funny Gen Z syntax anytime we want, so I don't want to get too caught up on this right now. Next, I want to change how the code should be run. Right now I have a working compiler that compiles to C code, but I want it to be either compiled to assembly or to be interpreted. Which should I choose? I mean, this part should be obvious, right? It's a final project for a not so important course with less than 2 weeks to implement. Clearly it's going to be interpreted, right? Then you'll be absolutely wrong. My Asian mom would be extremely disappointed again if she found out her son chose to make an interpreted language instead of a compiled one. So yeah, I decided to compile it down to x86-64 assembly. Finally, I need to give you a name. The language is basically an amalgamation of Basic and Lua, and it's written in Python. So it's either going to be Pasic or Pua, and I choose Pasic. With all of that decided, I started implement lexer, the first part of the compiler, because a typical compiler is made of 3 parts, the lexer, the parser, and the code generator. The lexer takes the source code and breaks it into tokens. Tokens are just tiny pieces of text that mean something, so that the parser will understand the source code. Let's take the following math expression as example. 40 plus 29. The lexer will break the expression to something like this. Each token has information about its type, literal text, and position in the file. For other tokens like parentheses or brackets, I'll also add them to the symbol type enum. For keywords, I'll create a separate keyword enum, and also a lookup table in order to easily determine the token type. And then the lexing process is essentially one big if-else clause. It checks the current character, determines the corresponding token type, and then advances to the next character or token. And if it lex this code, it will turn into this pile of tokens, which is exactly what I want. Now that our lexer can lex the tokens, we can try to parse them. The parser will take the tokens and based on some grammar rules that you defined, convert them to some form of intermediate representation. You might heard of a thing called abstract syntax tree, AST for short. That is the representation my parser is building. The original tutorial didn't build any form of intermediate representation actually. It utilizes the call stack of our parser to implicitly build the parse tree as we go. Basically, instead of generating an intermediate representation, it generates the compiled code as it parses the source code. But it's totally fine. I can just modify it to generate the parse tree. Anyway, first thing I want to do is to make the hello world to work, because I want my program to output something to make me not feel like a dumbass not doing anything. This basically means I had to implement the print statement. So I'll quickly lay out the grammar. I define the argument for print to be an expression because I want print to support printing strings, numbers, and identifiers, which are all expressions. And then here's a program that prints string, number, and identifier in Pasic. And the parse tree for them will be similar to this. And I'll define a statement node class and expression node class, and a function called statement, which will determine what type of statement we should return. Now each time we encounter print, we will match with left parentheses an expression and then a right parentheses, and then generate the node. And what is an expression? I took some inspiration from C and Python grammar and came up with this. It's kind of complicated, but I'm only interested in the strings, numbers, and identifier right now. So I'll modify it to ignore the rest. And I'll define each line of the grammar definition to be a function, just like any tutorial will teach you. For a non-terminal case like expression, simply call the next case, and for a terminal case, construct the node and return. I'll ignore the case of identifiers for now because I haven't implemented variables yet. And finally, there's the intermediate representation for a single print statement. If I had chosen to interpret the language earlier, the rest of the process would have been pretty easy. We'd simply evaluate each expression node and print it using Python. But no, I decided to compile this shit. So let's generate some x86-64 assembly. Okay, so the code generator receives the intermediate representation of a print statement. It will first evaluates the expression. So I'll write a function called toPostFix, which basically converts the parse tree to a linear list, specifically to the reverse polish notation or postfix notation. The algorithm is essentially a post-order traversal of a binary tree. That is, traversing the children first, then the parent. After that, depends on what type we are printing, we're doing different things. For printing a string, we first need to reserve space for a string literal in the data section. So I convert the string to raw bytes so it automatically supports escape characters. After that, I can pass in the pointer to the string in RSI and length of the string in RDX, which is calculated in Python and just call write syscall. For printing a number, we first emit the postfix notation by doing stack operations. I'll write a function called emitExpression that does that. Right now it's only a single integer, so we simply push it onto the stack. And then we need this monstrosity. This is basically a C function that I compiled to assembly. It takes an integer as an argument, convert it to string, and print it to stdl using write syscall. Now we can pop the expression result to RDI, which is where the first argument lives, and just call the function. For identifiers, I'll skip them for now. Then we can finally write the generated assembly to a file, compile it and link it, and there we go. A native executable that prints strings and integers to the terminal. And holy shit, that was a lot of work. But I'm not done yet. Remember in the beginning I showed a program that runs Game of Life? Well, in order to do that, we need a language to be Turing complete. Not gonna explain what that means, but we'll need condition, loops, and some kind of access to memory. Okay, let's do variable assignment first. And also all of the arithmetic operations because they will be useful in the future. So I'll extend the grammar like this. Also the grammar of declaration. And again, each line of definition corresponds to one function definition. For the let statement, we first check if the first token is a keyword let. Consume it, next consume an identifier and add it to the symbol table. Consume an equal, finally parse an expression. For expressions, we call the next definition until we hit the terminal case, and parse the next element based on the next token. But why can't we just define all the operation in one line? This is because of operator precedence. Essentially, the lower the operator's position in the grammar, the higher the precedence, which means that they will be evaluated first. Now for their assembly. I'll store the variables on the stack by maintaining each variable's position relative to the base pointer, RBP. First, I'll sync the RBP and RSP. This is to make sure they are at the same position when the program starts. Then I'll keep track of the space that the program has used. Initially, it will be 8, because RBP itself is an 8-byte number, and a symbol table for each variable's position on the stack. And every time we encounter a new declaration, we can evaluate the expression, move expression value to the current stack position, and finally update it. Now if any variables comes up, I can just look into the table and get its value. But we have a problem. We will use the stack when we are evaluating expressions, but our stack pointer RSP was never updated. So if we push anything onto the stack, it's gonna override our variables. And I spent an insane amount of time debugging to the point that I started to believe in God because I was literally praying. So yeah, simply subtracting the RSP by some padding at the beginning solves it. I'll do 1024 bytes for now, but this means I cannot have more than 128 variables, which I think is fine. I can optimize it later. Now I'll take care of generating expressions. I already had a function called emitExpression at this point. Right now it pushes integer onto the stack when encountering. To handle operations like plus and minus, we can make it pop 2 integers off, do the operation, and push it back onto the stack. Luckily, x64 has all basic arithmetic operations built in, so generating assembly is pretty straightforward. And that is variables done. For the following program, it spits out this pile of assembly. And since I use the same mechanism for evaluating expression in print statement, the rest automatically works, which is nice. Finally, condition and loops. They're really similar. An if-else statement is just conditional jumps to instruction label. Loop is the same, but instead of jumping back to the end of block at the end of body, it jumps back to the start of the loop. And again, I'll define the grammar for if-else statement and add support in the parser. Each statement node for if is going to have a condition, which is an expression, a body, which is list of statement, and an optional field called alternative. That is to save the list of the next elif clauses if the condition evaluates to false. And if we try to parse this program, it will generate this parse tree. Next, I can define the while statement. Its statement node will be very similar to if-else with a condition and a body. And let's generate assembly for them. In x64, we can jump to arbitrary label or address using the JMP instruction. Not only that, there's a whole family of conditional jumps for us to use. They jump based on the state of particular processor flags. The one I'll be using is the JE instruction. Since our expression always evaluates to some value, we can first pop the result to rex and just do this, and JE to the next instruction. And every time we encounter the end of body in an if-else clause, we'll need to jump unconditionally to the corresponding end block. But how do I know which address to jump to? Well, for that, I can just maintain an address stack that keeps track of the next jump point. While statement is very similar, but at the end of body, instead of jumping through, it unconditionally jumps back to the start of the loop and checks the condition again. And when we compile this thing, it doesn't work. Oh, I just did an increment X. Classic programmer mistake. Let's go! And believe it or not, the language is Turing completed. How do I know that? Well, if a language can write other Turing completed program, then itself is Turing complete. And one common test is to write a cellular automata program. One of the easiest is the rule 110. So let's go. Now I can finally implement the ultimate goal, the legendary game of life. It is more than just a coding challenge. It is a timeless classic, a sacred tradition among programmers. And now, my very own language is worthy of it. But before that, I'll quickly add macros, lists, and arbitrary memory access just to save myself from unnecessarily pain. Then I'll get to work. And there it is. a language that compiles to x86-64 assembly implemented from scratch, just for the final project. I know it's kind of shitty, it doesn't have a structure support, no namespaces, no type checks, and if you define more than 128 variables in a function, you'll get stack overflow, but it's just a final project after all. Oh, and for interested, I got an A- at the end. Given that I figured out the midterm and assignment, I'm pretty satisfied with the result. So yeah, happy ending. I'll put the repo in the description, and good luck porting Doom on this thing.